Um, so this seemed like pretty straightforward operations that we've seen before. If you've looked at Fast AI or if you've looked at scikit-learn, it's just the operations that you recognize this as the operations that you do on your data to create a batch to prepare it for processing. There are a couple of, and you can see that the functionality follows what you've seen on scikit-learn, except now it deals with tensors instead of arrays. But there are some extra bells and whistles that it has that allow you to handle large files, which normally wouldn't. Where if you have lots of data that you couldn't fit it all in your memory at once, it gives you a way to deal with that by breaking it down into a number of files and drawing samples at random from those files to create your batches. So that's basically what we've run through in this, in this section. They just coded up an example to do that for the California housing data. Does anyone have any questions before we start looking at the notebook? Okay, let me stop sharing clock and start sharing the notebook. I can't find the notebook. All right. I don't want that. Hold on for a sec while I get the notebook. Let's see. Okay, are you seeing the Jupyter directory screen?
Yes.
Okay, let me just start up. I thought I had this notebook started up. Oh, I know, I had it on, I tried to run this notebook on my machine, which is Windows 64-bit and so on, but it ran into some trouble. I couldn't execute some of the cells, so I ended up having to run it on Colab. And now I'm not sure where it is. Let me take a look around. Not that one. Not that one. Not that one. Well, I think what I'll do is I'll just bring up the notebook and then go straight into Colab. So there it is. Okay. So does everybody see that notebook, chapter 13 notebook?
Yes, sir.
Yes. Okay. Let's go into Colab and just run it in there. Let's see. I might have one that I already opened. Opened. This is the one. Yeah, that's the one. Okay, I just made my own copy. I made my own copy previously and saved it on my Google Drive so I can make modifications to it because I had to make a few modifications. So let's just start running this thing. Okay, I think it's just downloading something. That's pretty quick though, so it won't take long. Okay, I've seen this error before. It doesn't seem to interrupt the ability to execute this stuff, so I'm just going to ignore it. So all it's doing now is it's generating a little fake data set with 10 tensors with numbers 0 through 9 in it. And he says, so there's a couple ways. So there's two ways you can do this. You can either, create your tensor array, and then create a data set using this data set dot from tensor slices method applied to X. Let's just see that for a sec. See, it's a method that, well, anyway, create a source data set from your input data. Then it shows you right away that there's another way you could have done, a simpler way, maybe just tf.data.dataset. You use that method and then just chain it with the data set that you have, and it'll do the same thing. So now what you got is an iterator. The data set now is an iterator, and you can iterate through it, and it shows you, it's basically the integers from 0 through 9 data set. Okay, and now it's got this method a built-in method where you can create epochs and batches out of your data. So, normally if you have, in a real data science problem, you'll have like, thousands of items or whatever, and you want to, and each group of input items, your whole data set is called an epoch. And generally when you run gradient descent, you're going to run it on an integer number of epochs, and each epoch is going to be split into batches. So this is the way to do that. You have these methods called repeat and batch. So repeat basically makes 3 copies of your data. Actually, it doesn't make real copies, but it uses your data 3 times. It runs through your data 3 times, and then the .batch method says, okay, now make batches of size 7. So, if you had 10 items in your data set, and if you repeat those 3 times, that's 30 items, and then you divide that into batches of 7, you're going to end up with how many batches? Anyone?
4.
Yeah, you're going to have 4 batches with a leftover, right? So you'll have 4 batches of 7, but then there's an extra partial batch at the end, and it has 2. So 4 times 7 plus 2 adds up to 30. As you can see, they're all ordered. In this case, they're all ordered from 0 through 9, 0 through 9, 0 through 9. And then he mentions that sometimes you might not want that extra partial batch. So there's actually a switch that you can tell it to ignore the partial batches. I forget what that switch is, but it's possible to do that. Then he shows a bunch of other methods for building up your data sets. And one of them is the .map function, which you may be familiar with from pandas. So you can apply this lambda function to each item in the batch individually. So it basically says, give me the square of each item and replace that data set with this new data set. And so, you can see what you get. You get the squares from 0 through, let's see. Oh, it's not squares. I'm sorry. It's just multiples of 2, right? So you get multiples of 2. You get the even numbers up to 18 now. So that's what you expect. Then it's got this weird method. I'm not sure why you would use it, but there must be a reason. It's called unbatch. So you can pass it a data set that's been batched up, and it will unbatch it to singleton tensors. So you do that, you can, so when you've done that to your data set, now instead of having 4 batches, it's going to have 30 single tensors. Let's just verify that for ourselves. We can go, at least that's what I expect, it's going to have 30 scalar tensors. Oh, 10. How come it only had 10? Tensors.
I don't think you've run the cells in between with repeat and.
Sorry?
I don't think you've run these cells in between.
Yeah, but the data set that we created already had done that, right?
The original one had only 10, right?
Yeah, but I thought
we didn't hit repeat.
Oh,
That's
At some
the
point
third.
we said we replaced the data set with a new data set.
Yeah, you haven't run that cell.
Oh, I haven't run that yet. Okay, right. Thank you. So let's do that. Okay, so now we'll catch up with where we are in the notebook. And now if we do the unbatch, we should see a data set of length 30. Oh, didn't like that. Data set length is unknown. Uh-oh. Data set equals, I have to start again. Maybe an iterator doesn't have a length or something. Let's see.
You're probably better off trying to just print it, I guess. Just
Yeah.
copy that print, yeah.
Yeah. Okay. Okay. So now we should just do print the data set. Or I think it doesn't want to. Yeah, we can't just print it. I think we have to actually cycle through it like this. Yeah. So now we see 30 tensors. You know, and they cycle through the even numbers from 0 to 18. So now we understand what that does. Now there's this other method that applies a transformation wholesale to the whole thing all at once. That's what this dot filter method does. And it's similar, you know, this map method you may or may not have encountered in pandas. It does the same thing in pandas, and this dot filter method also is copying the functionality of the dot filter method in pandas. It's basically applying an operation, a lambda function, to the entire data set all at once. So let's see. We saw the map method. Now we're doing the filter method, and this operation is a Boolean operation. It's just keeping the items that are less than 10, because lambda x show that x is less than 10. So, and then there's this dot take method that allows you to take them in groups of that allows you to take a certain number of those out of your data set. So so now we have this data set, and we can convince ourselves what it looks like. Just put a code cell down here and do the same thing. Let's see what it looks like. And so let's see. Oh, and it's supposed to only keep things that are less than 10. Wait a minute. Data set equals data set. Did I do this? Let's make sure yeah. So you can see it only kept the, it threw away the 12s, 14s, 16s, and 18s. And 10s, I guess, because you have to be less than 10. So you can see everything is less than 10. And now there's this dot take function that basically takes 3 off the top. So this is kind of like a stack or something, and you can take the first 3 items, which are this one, and this one. So that's what you get when you do this, when you use this take method. So we're basically just learning a little set of methods that we can use on to create our batches. Okay, now what's this going? Range 10. Okay, so now we're going back. First, we're setting a random seed because we're going to be doing a shuffling the data here. We're going to start the data again, just like we did before, counting from 0 through 9 and repeating that 3 times. But then this time we're using this shuffle method. And the way it describes the shuffle method is that it has a buffer, and it takes, let's see, it randomly chooses a bunch of items and fills from your data set and fills the buffer. And let's see, let me go back to actually how it described this, because it was a little bit confusing. Let's see, shuffling the data. So he says you must specify the buffer size, and it is important to make it large enough, or else shuffling will not be effective. And then he gives this example of shuffling cards 3 at a time, and then the question at the end, this is the little footnote on page 417, or if you have the Kindle book, it's sort of right after the beginning of the shuffling the data section. He gives an example of trying to shuffle a deck of cards, 3 cards where you just get to pick 3 cards and shuffle them each time. And then he asks the rhetorical question, do you think it will be perfectly shuffled when you're finished? And so you can think about that. But so the idea is that you define a buffer size. In this case, our data set has 30 elements in it, so we define a buffer size of 3. And the way he describes it, let me just read what he says. A simple way to ensure this is to shuffle the instances using the shuffle method. It creates a new data set that starts by filling up a buffer. In this case, our buffer is size 3, with the first elements of the source data set. Then whenever it is asked for an item, it will pull one out randomly from the buffer. So we saw this operation of take 3 just before the shuffling the data section. And that's what this shuffle operation does first. It takes 3, in this case 3 because 3 is the buffer size, but in general it would take buffer size elements out of our data set in the order that they were given to us, and then it would shuffle those and return them as they're asked for. And then when you, and each time it returns one, I guess it says that it, so whenever it is asked for an item, it will pull one randomly from the buffer and then replace it with a fresh one from the source data set. And it keeps, so you can keep asking it for new items, and it will keep performing this process where it draws a new item into the data set, shuffles everything, and gives you a new item back. And you can keep doing this until it's gone through the whole data set, until it's empty. So let's see. So it says you have to specify the buffer size and you have to make it large enough, or else shuffling will not be very effective. And then it gives the example of shuffling a deck of 52 cards with a buffer size of 3, which isn't going to be very effective. Okay, so then this example here is the first use of shuffle. We see how it works. First we generate this data set, then we shuffle it using a buffer size of 3, and we ask for a batch of 7. So the data set now has 7 items in it, and you can print that batch. And it's not just asking for a single batch, it's asking us to go through the data set and create as many of these batches of size 7 as we can. And because we haven't told it anything different, we haven't told it to throw away the partial batch at the end, it'll return that too. So now you can see that it is giving us randomized batches, which is good. That's kind of what we want. And then it returns this randomized batch at the end. And then let me just go back and mention this way that you can get rid of that extra batch. He mentions that drop remainder equals true. When you iterate over the data set, you can let's see, not range 10, repeat 3, batch 7. I think here's where you do the drop. You can say drop remainder equals true, and then it will only return the full size batches. Well, let me see if that's where, I'm not quite sure if that's where. Let's try this experiment, because I'm not sure where you put that drop remainder equals true in. Maybe it's after dot batch shuffle. Blah, blah, blah. Yeah, maybe it's in the. I think it should be in the batch, within the batch command. But
it goes in the batch itself.
Yeah, that's what I thought. So let's just see. Yeah, and now it gives us just the 4 batches, and it threw away the extra one, right? Okay, so
I have a question there actually. So with buffer size, should that be like the size of your batch then for it to do something meaningful?
A good question. I think it should be bigger than. Yeah, that's a good question.
I'm just trying to think about what would make more sense.
Yeah. I mean, the buffer size, it seems to me that you would choose a buffer that's kind of like as large as you can fit in your memory or something.
True. That is, yeah, that's what I think he mentions too. But I'm just wondering, like, if it becomes smaller than too small compared to your batch size, then does it become inefficient, or is it
Yeah,
just something not to worry about? Just shuffle it and then go on.
that's a good question to think about. In this case, our batch size is 7, but our buffer size is smaller than our batch size. So, um, hmm. Yeah, this would seem to conflict with his example about the deck of cards, right? We have a deck of cards and we want to shuffle them, um, and we just use a, a buffer size of 3. We wouldn't get a randomized deck at the end of it because
Right.
if the deck were in some kind of order to start with, and you just shuffled them 3 at a time, neighboring batches would still be sort of neighboring. You'd have a 1, 2, and a 3, and next to a 4, 5, and a 6, and the 1, 2, and 3 might have a different order. You might have 2, 3, 1, but it would still be next to the 5, 4, 6 batch. So it wouldn't be very random.
Right. That's what I'm kind of confused with how this
Yeah,
buffer works.
yeah.
Because if you look at the example, I may be wrong here, but if you look at the example in the Kindle version, the
Hmm.
very first batch that he generates, the numbers are all in increasing order. It goes 0, 2, 3, 6, 7, 9.
Yeah.
But the one you are generating for some reason is showing 1, 3, 0, 4, 2, 5, 6.
Let me find that. Let's see. You're looking at.
This would be, yeah, again, just shuffling the data right about the tip. And that is page number.
Yeah, I see. Shuffling the data, and then we see those batches next. This size 7 batches.
Mm-hmm. And if you look at
Yeah,
the very first example that he's printed out, the first batch, it goes 0, 2, 3, 6, 7, 9.
yeah.
Um,
So we.
Yeah, what confused me, Rekal, was he says that the buffer is filled sequentially, then
exactly.
shuffled. So
Exactly.
if the buffer is filled sequentially, then you would fill always sequentially, then you would fill
Exactly.
the first 5, then the
Mm-hmm.
next fill would have to be from the next 5 of the sequence, right?
Next 5, or are you just dropping the first one and then 5?
Yeah, meaning from when I say the next, I mean drop the first 5 and take the
Oh,
next 5 from the sequence.
okay. I was not thinking of dropping the first 5, the original 5. I was just dropping the first one from the first 5. So you still have 4, and then you just add the 6th one in there.
Yeah. Until, but if you're given a batch of 7, do you
No,
process it?
so you've already gone off to batch. You're still stuck with how the shuffling of it, right, in the buffer size. So we're wondering how the buffer size gets fit. So from what Joseph read and what's written and what I understand was that if you have a buffer size of 5 over here, you'll put the first 5 elements, and then whenever you call, you keep getting one element at random, right? From that buffer. Isn't that what's happening? Or am I wrong over there?
Yeah, it sounds like you would first get you would first draw the first 5 elements, which are what are they 0 through 5, right? And then you would shuffle them, um, and then you would start returning them. But each time you return one, you would draw in another one. You would draw in the next one, and then uh, would you shuffle it again, or would you?
Yeah, I didn't understand the details there.
And that's where I was confused from the example in the book, because if you do, like you said, just to add 1, then does the book example work? Because it does work because the buffer size is 5, so you
5,
do
yeah.
0 to 5, and then you draw the 6th one as the next one, and it's the very next one that you provide.
Right.
But then how does 9 get in there?
And how does 6 get in there?
So each time you ask, you don't give back 5 elements, right? Each time you ask, you get back only 1 element.
Correct. So
Okay.
6 and 7 make sense. The next can only be, isn't it 8? At
No,
most.
right? When you are at 7, you would have collected
Just one.
1, 2, 3, 4.
For you,
I see what you're saying. Correct. Yeah.
right? So it can't be 9 then,
Yeah.
if you're
That's
just
true.
adding 1.
Correct. Yes. Uh,
In fact, as Joseph said, then it also fails to explain how you get 6 if you're just, because 0 to 5 would be your first, no, 0 to 4 would be
4.
your first 5,
Right.
Yeah.
right? Then you would add 5. So how does 6 get in as your next choice, even if you shuffle?
No, not like that. For getting the first element, you'll have 0 to 4.
Yeah.
Correct.
When you move to the next one, you'll have up to 5.
Oh,
Okay, because
Yeah,
you'll replace 1.
Yes.
Okay, okay, got it.
You'll
Okay,
have
so
up to
then 9 is
6.
explainable.
Yeah,
Okay,
9 is
then 9 is
explainable.
explainable. Okay.
Wait. So 0 to the first one 0 to 5, right? Sorry, 0 to 4. The second
Right.
one 0 to 5. So that's good.
1 to
2 is
5
good.
rather.
1 to 5.
Right, because you would have finished using 0, right?
Yeah.
So
Okay, right. And then so you have 1 to 5, and then you shuffle those and return one
correct.
of them. So that can be a 2. And then the next one,
2
0
to 6.
through 2 through 6, so you can return a 3. 3 to 7, so you can return a 6. 4 to 8, so you can return a 7. Yeah, okay, that works. Yeah.
Yeah, so it should always be in increasing order, right? Oh, wait, this buffer size, he's used 5 one place and 3 in the other example, so that confuses.
But that may be because of the repetition, no?
Yeah, so that's what. So that's only after you cross 9 will it repeat, right?
Correct.
But in Joseph's example, which we're sharing right now, the very third element is the 0.
That should be fine, right? Because it's 0 to 5 that you, or 0 to 3 that he'll get.
But 0 would have
Because
already been dropped in the first one, right?
Why? What do you mean 0? He hasn't dropped 0 because he's given 1.
You return 1, yeah. So
Yeah, so 0 is still there.
No, correct. 0 is still there, but then I'm saying when you, so you got 1 because you looked from 0 to 4, right?
yeah.
And then you moved to
2. 0 to 2. Buffer
Oh,
size
sorry.
is 3.
Here it is 3. Correct.
Oh, in this case, yeah, 0 to 3. Okay. 0 to 2.
Yeah, so I still don't understand how that 0 comes.
No, so what's your question? Sorry.
So if you do the same calculation, so 0 to 2, you get 1.
Correct.
And you get 1 to 3, so you get 3. Then it's 2 to 4. How did the 0 come there?
But 0 is still in your buffer though, right?
You should have dropped that, right? Because your buffer size is 3, right?
Yeah, but you won't
I see what
drop,
you're saying. Right.
you won't
correct.
drop
Okay.
what hasn't been selected.
You
will
randomize.
pick
Yeah,
up
you
the next
randomize
one.
first.
Correct. Yeah. Okay, that makes sense.
Okay, so we can sort of see that a small buffer size is not doing well in randomizing. There's still some relationship between neighboring elements. And I guess that illustrates his point that you want to use a larger buffer size, I think. So I wonder if we skipped something. There was an apply method. I don't remember if I covered that. There was a map method. Yeah, here it is. The map method applies some function to individual element at a time, but then there's the apply function that applies, I think he didn't use this example. The apply function applies some function to all the elements in the whole data set at once. So, and we didn't really show the example of that, but in the book he talks about it. And then he talks about this filter method that applies some kind of a Boolean filter to your data, and that's how we reduce the data set size down to throwing out the larger elements. Okay, so then the next example he's talking about, okay, practical usage of this, of all of this is, suppose you have this, and of course this data set is not an example of that. This California housing set data set easily fits into memory, but he's saying let's pretend that we want to do this operation where we have this large data set and we want to split it up into large number of files and draw the data randomly from those files. And he gives us this method. He sort of outlines a method of shuffling things. And I'll just go through what my understanding of it is. He says the first thing you do is you apply this Python function, if it's a text data, for example, you apply a Python function called shuf, S-H-U-F, and you shuffle the text. And I guess shuf will allow you to shuffle a large text file in place, even though it won't fit in memory. I believe that's what that shuf command does. But then he says the next, so that's the first step. The second step is you split this text, if you're talking about a text string, for example. First, you use this shuf function to shuffle it. Next, you split this text, this very long text string into multiple files. You split it into chunks and save it in multiple files. And then you compose batches by this method that he calls interleaving, simultaneously interleaving examples from multiple files. So what that would look like is you would read the first line from 5 different files. Suppose you have just large slew of files all saved with pieces of this text string, right? And so you have this process where you interleave data from a set number of files. So let's say you said I want to interleave data from 5 files. So you choose 5 files at random, and then you choose their first line from each of those 5 files, and randomly combine them into one string. So that's what that process would look like. And then once you do that, you shuffle it again. So there's a lot of shuffling going on here. But that's my understanding of this process that he sort of outlines. And then now he's sort of going through this process with the California housing data, but it's not the same kind of, he talked about this example with a text string, with a data set that was a long text string, and this housing data set is something different. So now he's going to show how he's going to apply these concepts to it. So first thing he does is he does the train test split, and he splits off a training set and a test set, and then he reshapes it, and let's see, reshape -1,1. Somebody refresh my memory what this reshape does. He's going to test split the housing data. Oh, housing data this is the Y, the target, right?
Right.
So housing.target.reshape -1,1.
So it throws all of the other counts into the first dimension, and then the last dimension is the target. That's the 1. And everything else gets thrown into the -1.
Train test split of housing data, housing data dot target dot reshape.
So you want Y to be something cross 1. So that's all he's trying to do by doing that reshape. -1 is.
Oh, he's making it into a vector. He's making it into
all
a vector.
rows. Yeah.
Great. Okay. So does everybody see that? He's taking the data set, which comes in, I think it has 9 columns, and the 9th column is the target, which is the housing price. And the first 8 columns are the numerical features, I believe. They're all numerical features of the house. So there's 8 of them. So then this part is the features. Housing.data is the dot data. I guess this dot data method gives you it knows about this data. It knows how to organize this data set, and it knows that the dot data method returns the first 8 columns in this case, and the dot target method returns the last column, which is the housing price. And then, as Rekula and Srinivas said, this dot reshape forces it to be a vector, so that everything is, that the features are a vector and the target is also a vector instead of a scalar. Okay, and then he's setting a random state in that command as well. He does the same thing to the, then he splits this, okay, the first thing he calls the, sorry, I gotta do this. What did I do? He calls this thing x_train full and x test. So he's splitting off a train full and a test set, and then he's further splitting that train full set into a training set and a validation set, right? You've probably seen that before, right? So he's doing the same operation that he did before. Okay, now he wants to do normalization. So he defines this scalar, standard scalar, and remember what that is. It's going to subtract a mean and divide by a standard deviation. So he defines the standard scalar, then he applies it to the training set. He gets the mean, he gets the standard deviation, and remember that that's once you get those numbers from the training set, then you have to apply them whenever you process the validation set and the test set when you do the processing. So I'm trying to think here. We're trying to learn an application that splits this incredibly large data set into pieces effectively, and I don't understand how, if this data set won't fit in memory, then how can he get the mean and the standard deviation? In this case, it does fit in memory, so there's no problem. But if we're hypothetically considering a case where the data doesn't fit in memory, then I'm not sure how you get these numbers out of it. So maybe we just put that aside and think about that later, if anybody has any thoughts about that. Okay, so then for a large data set that doesn't fit in memory, you want to split it into many files and then have TensorFlow read the files in parallel. And he's demonstrating this. Let's start by splitting the housing data set and saving it to 20 files. So he builds this function, save to multiple CFE files. He gives it a directory. He gives it a directory name. Sorry, this just makes a directory name. And then os.makeDirs makes the directory exist OK equals true. I guess that means if it already exists, don't worry about it. Path format os.path join housing directory my 0 to 2d.csv prefix header n parts equals 10. I thought he wanted to split it into 20 parts. Name prefix.
He does do 20 later.
Yeah. Okay. My 2D. Oh, join. Okay, so he's building this path.join housing dir, which you defined here. My something blah blah blah. He's making a file name. He's making a file name here, I guess. We can see how that comes out in the end. So you pass in a data set. You pass in a name prefix, and that's what goes in here. You're telling it there's no header, that there's to be 10 parts. M equals length of. I thought that these data sets didn't like. Oh, in this case, the data set is just going to be an array, I guess, or a tensor. Let's see. Oh, in this case, it's just going to be a NumPy array. Let me run this thing. Downloads the California housing data set. Blah blah blah. Did it? Okay. Now you can ask for length of the data set, and it'll tell you how many. I think there's some tens of thousands. Let's see. Search code cell.
If you want to know the cardinality, it is the train set is 15480 by 8.
Yeah, 8. It's 15480. Is that what you're saying? Length
Yes.
of 15480.
Yes.
So that should be this length of X train. Oh, but the training set is only part of it. So 11,610. So
Yes.
it was 15,480. You say?
Yes.
Okay.
That's the full train set.
Oh, okay.
X train full. So.
Okay. And in this case, we told it to split. Let me go back and see what we train to split. I guess there's a default, right? What's the default proportionalities between test and train? Is it 20% for training or for test? I don't recall. Well, let me see. Len of X test and when you already told me this, Mayank, but I'll. Oh, let's see. There must be a default proportionality between test and train, and I think it might be 20%, but I'm not sure. Let's see. Okay. Okay, 11610, 5160, and 51548. Oh, so
I think so it's 0.225, 25%.
25%? Okay. Okay, that's
Um,
fine. Or is it 30? Oh, is it 30%? Because it looks like it's 30%, right? Because test is 5160 and train full is 15480. So it looks like it's, oh, you're right. It's 1/4 of the whole data set. That's right. So there's 3 parts to 1 part. So it's 1/4 of the whole data set. Sorry, you're right. Okay. So now, let's see. So this is a way to read in the data, and I guess you specify this in coding. I'm not sure why you have to specify that in coding. Maybe just for safety's sake. If you're reading real number, or you're reading floats, I think. No, maybe you're reading integers. Let me see.
He's reading as a string. That's why the example reference reading text makes sense, because he's pulling it in as a text file.
Okay. So reading UTF-8. Does anybody know what this means offhand, UTF-8? Is that just a text encoding?
It is a text encoding.
Okay, okay, great.
Coding.
So this thing,
So just to add, this is for the strings and the header files. The name is, I think so, the housing, how do I say it, the feature names and the
yes, and
column
so he
names.
says,
Yeah.
right, so he says if header is not none, so if there are column names, then you you write them. Let's see. So save to, yeah, so we're taking a data set and we're transforming it into text format. Is that right? Line by line, and saving it that way?
Right, that's what my understanding was, that he's reading it as a text file, the whole thing, and then for each of the 20 files that you create, you have to write headers if the header is present, and then copy whatever 1/20th of it and dump it into those 20 files.
Right, and in this case, header is none, so there won't be any headers. So
I think that's just the default. When he calls it, I think he does pass the next
okay, you can
step.
pass, okay, great. So you can pass in a header then, okay. And then, so if header is not none, then you first write the header, then you write a carriage return, and then for each row, you write that row. Let's see, comma separated text, join rep column for column and data row index. Rep is look this up.
Echoes the values as a string. So
Yeah.
it just repeats the column.
Yeah, it's different than str though. And one of them quotes, I think str quotes a string with its quotation marks. One of them includes the quotation marks and the other one doesn't. I'm a little bit not clear on that right now. Because repr of column is going to return a string, but I'm not sure why he didn't use str of column. Here it says return the canonical string representation of the object, or many object types, including most built-ins, eval. So yeah, so I'm not quite sure why he has to use repr instead of str, but let's just move on, unless somebody wants to comment on that. Okay, so we might just keep that in the back of our minds. Remember that we want to understand that, why he's using REPR instead of str. Okay, so this is the little function that writes in this case, it's going to write 10 files because n parts equals 10. Okay, so he's built the function. Now np.c. What does np.c do?
It's the same NumPy thing, Joseph, that in earlier contexts, I think you had referred to an easier way to do this than np.r underscore or c underscore. I forget what the new command is that you were referring to, which makes it simpler usage.
Okay.
It's just been a while since we encountered it.
Yeah.
Like you said,
Let me
for
quickly
I
look it
think
up.
it's
Adding an access.
concatenation. Yeah.
Pardon?
I think it's adding an
Concatenation.
access, right, Mine?
Yeah.
Say that
Same
again?
thing, adding an access. You remember you were referring to Jeremy's technique of doing colon, comma, none. So wherever you put none, you basically are adding that access of 1 over there.
Oh, okay. So that's what we're doing here. Let me go back. Find where I was there. Okay. Train data np.c of x train, y train. So these are already arrays. These are already vectors, right? X train is even tells us it's 11, 6, 10 by 8. Y train is 11, 6, 10 by 1. Remember, as Raquel reminded us, we made it into it was a scalar, it was a 0-dimensional vector, but now we gave it a one, we gave it a, sorry, it was a 0-dimensional scalar and we turned it into a 1-dimensional vector by adding that extra 1 axis. Okay, so now we're going to do np.c. We're combining these into a
it's like stack or it's
stack
or restack.
Okay. Oh,
like
okay.
Combining them.
Okay. Let's just convince ourselves that we're understanding what it's doing. First, we can do x train. We already know what the shape is, but dot shape. And then, okay, and now we can execute this thing and look at, oops, save to, we have to do this. I didn't execute that cell. So now we can run this, and now we can ask ourselves, what does this object train data look like now? And so if we would, I guess we would think that it's, I'm not sure what it would be. Let's just do it. I'm sorry, I wanted to do shape. Oh, it doesn't have a shape. Oh, I know, yeah. Yep. Okay, so it basically just stacked them, as Srinivas said. It stacked them into one. So, okay, so it basically just recombined them into the original form of the whole data set. I'm not sure why it did that. Let's see. I ended up having to do, this is why I had some trouble, even in the Colab notebook. I had to install, then uninstall pandas, and then install it again, and then restart the runtime. It was a pain in the neck. I hope it's not going to make me do all that again. Let's see. Okay, so we have created this train data object, and we've also created a test data object. We've created header columns. We've created a header. Let's just look at the header for a sec. Insert code cell header. Okay, so there's the eight columns: media, income, house, age, rooms, bedrooms, population, occupation, latitude, longitude, meet, and house value. So it has 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It has 9 values in it. Okay, that's fine. And now we should be able to get these file paths that we created in this function too. So this should be a list of, it's a list of files. How come it has 20 and I don't understand it. So he did say 20, and he did create 20, but n parts equals 10. I'm a little confused about how he got
Default
20
value.
files.
That's
Pardon?
just the default value. You're
Okay, that's
passing
the
in
default.
20.
And he passed in 20 when he actually called it. Yes, thank you. Okay, so then it generated these file names on the fly and saved them. And so now we can look at, we already saw the whole list of them. We can look at the first one. There it is. So there should be a file there. Let's see. Let's verify for ourselves that there is a file there. And let's just see what we have in there. And indeed, they're there. All the 20 files that we generated are there. So now I'm going to get back. Undo what I just did. Okay. Okay. Now, why did I have to? I thought I already imported pandas. Let's see. Okay, so this command reads the first file and just shows us the first 5 lines of it. I hope it's going to work. Good, it did. So there's that. So we wrote the header, we wrote and we wrote the data into those things. And this is this data has been, let's remind ourselves, it's been shuffled at random from our original data, right? Somewhere, I'm trying to remind ourselves, did we use?
I don't think we shuffled it. Right?
We didn't shuffle it. Erase, but okay, so we didn't shuffle it then. Okay. Okay, so there it is. Text mode with open. Okay, so with this context manager kind of language, with open train file path 0 as f for I in range. So now we're just opening this thing as a text file, right? And we're just looking at the first 5 lines. And we see that we wrote it as a comma separated list, just as we meant to do. We wrote it as a CSV file. Okay, we already did this. Okay, so then list file. So there's this command tf.dataset.list files, and you give it the file paths, and it will. It generates a data set. So it generates a data set given the. All you do is give it these the list of files that you gave it, and you give it the file paths. This list file command, this dataset dot list files method, actually goes in there, fishes out all the files, and creates a data set out of it. We've seen this. Jeremy does stuff like this in FastAI.
I think this dataset.list files is just creating those. I'm not creating, rather just reading in those file names, right? Because the very next cell you printed them, and it just prints those 20 files in some shuffled order.
Okay, for file path in file path dataset. Okay, I thought that list file. Okay, so the list files is just keeping a record of all the files, and it's shuffling them, right?
Yeah, that's what I thought was happening.
Okay. Okay, let's see.
Is it making? It's making them. Seems to be making them tensors.
TF tensor the 515. Yeah, that's weird. A tensor with a text string. Yeah. So why does it have to be a text string? P.
It's a file path, right?
Does anybody know what this B means. I've seen R, I've seen F. I haven't seen this
Binary.
B. Binary. Okay. So it's telling you that this is a binary file. That each of these files is a binary file, I guess. Let me see what it also what you can get out of this. Oops. File path dataset. File path dataset. File path is one word. Okay. So this object has all kinds of methods, including this interleave method that we talked about. And I do think that it's actually read in all the data. I'm not sure about that, but I think that this command does all of that. It reads in the data, and then you can apply these methods to it and get out and get the data back in batches or whatever. Let's just see how it goes. N readers equals 5. I think that's the number of files that you want to draw from in parallel. Because remember, I was telling you that outline of what he's going to do, where he's going to take, in this case, 5 files at random from the ones that we saved, and then read the first line of each file, and then make make a batch out of those and shuffle it. I think. Let's just see what it does. So the data set is file path. So file path data set now, well, if Reckel's right, then it's just keeping a record of where these files are. And then you apply this method, and and this is where it actually picks up the data and puts it together for us. File path TF data text line data set of file path.
I could be wrong, but could you do type on file path underscore dataset to see whether it is a dataset?
Yeah, good point.
It is a data set, right?
Because that's what I thought.
Yeah, so it's not just the file names, right? It did all that operation. It actually put together the data set for you, I think.
So when you hovered over file path dataset, it said shuffle dataset of 20 items, and those 20, I think, corresponds to the 20 file names, though, right?
Shuffle dataset. Say that again. I'm sorry.
If you just hover over the file path dataset variable.
Yeah.
I didn't see it coming up last time.
There
you go.
Shuffle
it says
dataset.
shuffle dataset with 20 items.
Yeah, and I think we saw it when we printed it out that it was
those
indeed
20
shuffled.
file names, right? Yeah.
As you said, yeah, and they're shuffled because there it is right there, all shuffled. So I think this file path dataset actually has all of the data in it, but I could be wrong. It could just have the directions for how to get the data in it.
If you go back to the book or the Kindle, and if you look at figure 13.2.
Okay. Figure 13. Where am I? Sorry. Am I near I'm not sure where I am in this book right now. Let's see, machine learning.
You're at page 52, so yeah, a while long way to go, I think.
Oh, okay. Can I, let's see, how can I tell it?
Search should work. Just try searching and.
Okay. What should I search for?
13, figure space 13 dash 2.
Dash 2.
Maybe that'll work.
See.
No.
0 results. Okay. Well, let me just find chapter 13 then.
Prefetching actually.
Chapter 13. Do that. Okay, now I should be close. So, okay. So you want figure 13-2. Figure 13.1. Okay. So this is the thing we did before, where we made 3 epochs and then we divided it into 7 batches. This is a nice schematic way to show us what we did. Now we're going to go to figure 2. This is it, right? Yeah.
Yeah. So there, if you look
So-
at the first part of the figure where it says list files, you see
Yeah.
that there are a bunch of those file names that are there.
hmm
So that's why I
There-
was thinking that list files is just
Yeah.
file names.
Yeah, it could well be that because it has all the information you need to generate the data set, right? It has the locations of the data files. So yeah, it may well just have it may well just be sort of the directions for getting the data. So then this part is repeat.
Because I think the whole point was that the data doesn't fit in memory. So you don't want list files to again have that whole thing which won't fit in memory. So it won't serve any purpose as well.
So it's a data set of strings pointing to the actual data.
File names.
Yes.
Yeah. Right.
Yeah.
That makes sense, both of you guys. Yeah, that makes sense, Rekil and Srinivas. Yeah. Yeah, because as you said, Rekil, the whole point of this is to get around the fact that you can't fit all the data in memory all at once. So yeah, it makes sense to just have a list where you can grab the files from, and then you can actually pull them as you on demand, right? Make up these batches on demand. So repeat, interleave. So in this case, the example is 3 files at a time, drawing the first line, which is, the 8 values plus the 1 label, shuffling them together, and why are you, I thought you were reading from these lines, not writing back to them. Or, so,
Yeah, you're reading and then shuffling.
yeah, so DFB. So I guess this is, so you can think of this as a machine that generates, okay, which 3 files am I going to pull from? And then after all that, it comes out, it decides, okay, these are the 3 files you're going to pull from. Then it shuffles, so you're going to pull the first line, the first example out of each of these files. You're going to shuffle them, pre-process them, batch them.
So question.
Yeah.
It shuffles and then it shuffles the order in which the files are read. There is no fixed order, correct? And then it reshuffles the lines that it takes from the files. Is that correct?
It looks like, because here's the dice, right? Here's the original files in order, right? And here's the dice that, I guess that to me, that means you're going to shuffle the order and you're going to pull 3 of them. And this is what the 3 that you got, the D, F, and a B. And then you pull the first line out of each one, and then you form that into, and then you shuffle them again, and form that into a batch of 3, I guess. Does that make sense?
Yeah, that's my understanding. I just wanted to make sure that's correct.
Yeah, and then there's this prefetch operation. Oops, sorry, back. And there's this prefetch operation that makes use of the time, like while it's putting together this batch for you, it can be looking ahead and getting the information about the next batch, something about that. So here it says, by calling prefetch of 1 at the end, we're creating a data set that will do its best to always be 1 batch ahead. While your training algorithm is working on 1 batch, the data set will already be working in parallel on getting the next batch ready, i.e. reading the data from disk and pre-processing.
Joseph, the next picture he has explains it visually very well. It's basically what we do in hardware pipelining and stuff. It just overlaps, creates the overlap so you hide the latency.
Yeah, so that this means you got to have like multiple CPUs to do this, right? It's doing
multiple
it on
threads, so multiple cores
threads
or multiple thread support is enough.
Okay. So this is the diagram you're referring to, the figure 3?
Yes.
Okay. So let's look at this. CPU, it's preparing the first data.
Sorry, the one comment I would make is think of anything which is the black line without any operation as wasted time on
Yes.
that.
Yeah. So here you'd have to do everything in series. You prepare the first data set, you use it, then you prepare the next one, you use it, and so on. And so the black line is, as you said, you're not doing anything with the CPU during that time, and then you're not doing anything with the GPU during that time. So this is a way to be more efficient with your CPU cycles and your GPU cycles, I guess. So you're looking ahead, preparing the first batch, and then while you use it, you prepare the second. While you use it on the GPU, which means by use it, I mean do gradient descent or whatever, compute the next correction. During that time, you're preparing the next batch, and so on like that. Is that your understanding, Srinivas?
Yes, that's
Okay.
exactly what it's trying to do.
Okay.
And then you use multiple threads within CPU to really make it parallel processor. You shrink the prepare time in the second picture to even more so that you increase the utilization of the GPU.
Oh, okay. Oh, okay. So in this one, it's showing that there's still wasted GPU cycles,
Right.
but here there's less wasted of the GPU.
Yeah, because I mean, in hardware and in general, you want to keep the most power hungry or demand hungry thing fed to the maximum
Yeah.
to get your throughput the most.
So
So
you're
you want to,
feeding the GPU
right.
and keeping it full at the cost of wasting a little bit of CPU time, I
Yeah.
guess. Okay. Okay. Oops.
Feeding the beast.
The other thing,
Okay.
like what Srinivas mentioned, is look at how small prepare one became, right? Prepare one became smaller because of the multi-threading option. Prepare one becomes prep one, that much time lesser.
So if prepare one means preparing like maybe 7 items for a batch, then you can prepare those 7 items theoretically, or in principle, you could prepare them in parallel.
Yeah.
And that's what's doing here. I mean, in this case, it's like 2 items in a batch maybe, and then you get them at the same time.
Across the threads.
Yeah, good point. Okay, so that sort of illustrates that for us. Okay, so now I'm going to use this CSV reader dataset thing that we just created to actually build a dataset for the training set. Note that we do not need to repeat it as it will be taken care of by tf.keras. So there's so I guess this is it. Train set, valid set, and test set. And this puts everything, I guess this is what Jeremy would call a data loader, right? For each of for training data, validation data, and test data. And now you're ready to process the data. Model equals keras model sequential, compile, fit, blah, 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 evaluate, predict. So once you've built the data set, the data loaders, that's the process you need to go through. Once you have the data loaders, now you can go to the next step, which is building the model, fitting the model, evaluating the model, and predicting, and so on. Right. So I think that's what he's showing us here. TF record. So this is the next. Is this part of what we're reading today? The TF record. Let me see. TF. Putting everything together, prefetching, blah, blah, blah. No, TF record format, that's what we're going to start. We're going to start with this next time. So, wow, it's almost just exactly 2 hours. So that's perfect. Yeah, so this is where we're going to start next week. And what I would ask is that people go through and make sure you can run this notebook. Just make sure you can run it and play. As you run it, play with it and interrogate it and ask questions, like we did when we were running through it just now, and just familiarize yourself with it. And we'll meet again next Sunday to take up the next section. So next section, I plan to go through the TF record format section and part of the so there's a TF record format section with a bunch of subsections, and then there's a pre-processing the input features section with a bunch of subsections. And so I plan to go through the TF record format section plus part of the pre-processing the input features section, right? I'm not sure exactly how much of it, but so that's sort of the plan for next time. Okay. Any questions up to
I
here?
got one last question on
Sure.
13.2, figure 13.2.
Yeah. Go back to yeah. 3, 2. Yeah.
So
Are you seeing it now, right?
Right, yeah. So with the list files, we shuffle the order of the files and you have those paths. And then based on some parameter, you pick certain number of files. I think that's cycle.
Yeah.
How does this repeat work? Like, is
yeah,
this
that's what.
repeat
Okay,
for
that's
the
a good
whole
question.
files, or is it just for the files you pick? I'm kind of confused with that single arrow running through there.
Yeah, that might be the sort of the epic thing where you say how many times you want to go through the whole data set. But let's look in here. You gave it the n readers. Cycle length equals n readers. Data set formula. You didn't actually execute it all the way down here. Parsed fields. So here's where it actually uses the data loaders and train set equals x match x. So this is that whole function, right? You give it n readers, you give it n read threads. I'm not sure what. Oh, this is what you guys were pointing to, the threading, using the multi-threading. And in this case, we didn't tell it to do multi-threading, or at least when we defined the function, we didn't tell it to. Sysv reader say that it didn't give it any threads when it called it here either. So there's no multi-threading. Shuffle buffer size 10,000. So that's a big.
In this case, he's repeating it only once, so it's just no repeat. But
Oh,
I guess
okay.
he shows
Repeat
in the
equals
picture
1.
that he could repeat if you wanted to.
Right, so that's what. So does that mean the whole data set? Or I'm just trying to figure out in the pipeline what would
I think
be.
that's the epics. I think that's the number of epics, maybe, as we were. That might be the number of epics that you want. I'm not
No,
sure.
actually, the repeat is repeating the number of, to Rakel's question, wouldn't it be repeat 2? You'll have to try repeat 2, but repeat 2 means, that you ought to be able to duplicate A to Z in memory, or is it just that it will duplicate it, but then only pick up each of the sentences? That's something you'll have to play with to figure out. His question, I think, if I understand correctly, Rakel is asking is, does A to whatever, let's say 10, so A to whatever the, let's say 4, so A, B, C, D, and if you repeat, then is A, B, C, D as a whole repeated or A only repeated? I would think it would be all of A, B, C, D.
Yeah, that's what the thing is. Yeah, the figure is kind of not intuitive.
And then to go back to your first question, Rekil, you asked about the buffer size. And in this case, so we have a data set that's 11,000. So I think he chose this to pretend like we can't fit the whole 11,000 of them in the memory. So he made the buffer size somewhat smaller than, but I think that the idea is that you make the buffer size as big as you can comfortably fit into memory.
Right. Yeah, Mayank shared the GitHub TensorFlow's GitHub repo, and it says that for perfect shuffling, a buffer size greater than or equal to the full size of the data set is required. So yeah, push it as far as you can go. In other words,
okay, that makes sense. Okay, and then so parse threads. I'm not sure what parse threads means.
I think that's again used for the multiple stuff. That's threading. In the third line you're doing, right? Dataset map reprocess.
Dataset map preprocess num parallel
so
calls. Oh, num parallel calls. Okay. Okay, if that's num parallel calls, then what is the n readers?
There are two parallel. Oh, n readers is just how many files you want to read.
How many files, right?
Yeah.
Okay.
So
and
out of 20, case, we are picking 5 randomly. That's
right, and in this case, you're reading them all at this. You're reading those 5 files in parallel with each other. So so this number is the same
No,
Is that reason why? Is that the reason why these two numbers are the same?
No, that's a different number, right? You're passing two
Right.
different things to two different places. There's
Okay.
end readers, which is
Okay.
number of files you want to read.
Yeah.
There is end read threads. That is the one that is getting passed to TF data text line data set as
Yeah.
the num parallel calls, which is again for parallelizing, but he set it as a different parameter.
And in this
then you
case, he
have
doesn't use it.
I don't know what none actually is. Is none like -1 in?
No,
Or is it just none? I don't know.
it's just none, and then you can, if it's not, that means it's not set so that you don't.
I guess then it's not parallel, right?
Yeah.
It's just reading them in sequential fashion.
CSV
yeah, use single thread if not.
Right. Okay.
So okay,
But
so here
map is being done parallelly.
Map preprocessed number of calls equals parse. Okay, so as you point out, then end parse threads is just being passed to the map function.
And I think it makes sense what you're saying, right? Preprocess will want to be applied to each file, I would imagine. So that's why those two numbers match, or is that just coincident?
Yeah, preprocess, as I think covered in when we covered on Sunday, but my understanding, preprocess is like basically normalizing.
Yeah,
category.
it's the standard scalar thing.
Yeah, yeah. So you would apply it in parallel to all of the multiple elements or multiple files in multiple columns of multiple files in parallel.
Yeah.
If you can do that.
Oh, so actually, sorry, I don't think end readers and end parse threads need to be equal then, right? There is no reason.
Have to be equal, you mean?
And don't have to be equal is what I'm saying.
That's correct. Yes.
Yeah, because you're just telling it how many files you want, and you can say you want 10 files, but I only want to read 5 of them at a time or something like that, right?
I think it's like an end readers is going to read from 5 files, but when you read from files, your interleaving process is just going to read one row from each of these 5 files.
Yes.
Get combined.
Yes.
You shuffle that in a batch and form your batch. So now let's say you have a batch of 32, and now you want to do pre-process, which is through this map. And then you're saying that, okay, give me these many threads and parallelly process these 32 elements in the batch. So yeah, there's no connection between.
I see. There's they're parameters for two separate processes.
Right.
Okay.
That's my understanding. Yeah.
Yes.
That makes sense. That makes sense. Okay. All right. Well, if there's no other questions, we can adjourn until Sunday. And have a great